Okay, in this video I will be going over section 5.3, and so this is going to be on independence and the multiplication rule. So let's go ahead and get started. So just a quick review of some things we've talked about up to this point. So we have the addition rule for disjoint events to compute the probability of observing an outcome in event E or event F. Remember, with OR probabilities, we want to think addition. And in fact, the probability of E or F is the probability of E plus the probability of F, given that events E and F are disjoint, meaning they have no common outcomes. Now, if they're not disjoint, then we use the general addition rule. And so that's P of E plus P of F, so the same as the above, but minus the probability of E and F. And then finally, the last rule we discussed in section 5.2 was the complement rule. When you know the probability that some event will occur, and you want to know the chance that it will not occur. And so the probability of the complement is 1 minus the probability of event E. So the probability of the complement of E is 1 minus the probability of E. Okay, so let's go ahead and move on. So in section 5.3, we're going to talk about independent events again. We said two events, actually this is the first time we've seen this here. So previously we were talking about whether or not events were disjoint. Here we're talking about what we mean by independent. So two events are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. In determining if two events are independent, ask yourself, is the probability of one event affected by the other event? Okay, so we'll look at some examples to figure this out. So first of all, let's look at these events and see if we can figure out whether they're dependent or independent. So tossing a coin and drawing a card from a deck. Now let's say I toss a coin and I get heads or tails, it doesn't really matter. That's going to have no impact on the probability when I draw a card from the deck. And so these are independent events. Drawing a ball from a bucket, not replacing it, and then drawing a second ball. So these would be dependent. Because if you think about it, the first time you draw from the bucket, let's say you have 20 balls, but by not replacing it, when you draw the second time, you only have 19 to choose from, and so your denominator is going to change for that probability. So here you do have dependence. Getting a raise in salary and purchasing a new car. Well, I think there's a good chance if you get a raise in your salary, you're more likely to purchase a new car. So this would definitely be dependent. By the way, if you haven't already, you should try these on your own and then check the answers. Having a large shoe size and having a high IQ. I don't think those are related at all, so we would say independent. Either one's going to have an effect on the other one in terms of any kind of probability. A parent being left-handed and a child being left-handed. Now there's probably a good chance that left-handed parents have more children that are left-handed. I don't know that for certain, but that seems to be reasonable, and in fact that is the answer here. We're going to say dependent. So it must be more likely that the child's going to be left-handed. Number 6, driving on ice and having a car accident. Well, if you drive on ice, you're probably going to affect your probability of having an accident. So this is definitely dependent events. And finally, winning the Mississippi lottery and winning the Florida lottery. So in this case, those two have nothing to do with one another. You might win the Mississippi lottery, and that'll have nothing to do with your chances of winning the Florida lottery. You just buy a ticket. So these are independent. If that dog keeps barking, I'm going to have to shut the door. 5.3, disjoint and independent events. So I just want to mention this. Disjoint events and independent events are very different concepts. Remember, disjoint events have no common outcomes. With independent events, the occurrence of one event does not affect the probability of the other event. If two events are disjoint, then it turns out they're not independent. So we'll look at that in just a second. When two events are disjoint, the occurrence of one does affect the probability of the other. So let's see that in this example here. So a die is rolled. Let E be the event that an even number is rolled. Let F be the event that an odd number is rolled. So these events are disjoint. Why? Well, they have no common outcomes. However, if the die is rolled and an even number comes up, so basically event E would be the first event, well, that means an even number came up, which means the probability of an odd number being rolled is 0. And so the occurrence of this event has a definite impact on the probability of the second event, rolling an odd number. That should be another D right there. Okay, so that's just something I wanted to mention, not all that important, but the author mentioned it. I thought I probably should. But what we really want to focus on here is the multiplication rule for independent events. If E and F are independent events, then the probability of E and F is equal to the probability of E times the probability of F. And this rule can extend to 3 or more events. So if you had the probability of E and F and G, I would multiply 3 probabilities out. Okay, so remember we said when you see OR probabilities, think addition. When you see AND probabilities, I want you to think multiplication. You're going to multiply. All right, let's move on to the next slide. And so, let's see. I actually had a worksheet, and the problem that we did, or the ones with dependent and independent I did earlier, we're actually on number 2 here. So I'm just going to go ahead and switch here to number 2. So it says about 13% of the population is left-handed. If 2 people are randomly selected, what is the probability that both are left-handed? First of all, are these events independent? Well, the fact that they say 2 people are randomly selected indicates that they're independent events. Like they're not parent and child, anything like that previous problem, or like what we had up here in this problem here. They're just 2 randomly selected people. So the probability of left-handed, I'm just going to use L for left-handed, and L is the probability of left-handed. Actually, I'm writing this in the wrong spot. So we said yes, they are independent, and that's because of the fact that they're randomly selected. The probability of left-handed and left-handed, I'm just going to write P of L. Whoops. Let's make an and in here. P of L and L. We'll just use that for the probability that you pick a left-handed person and then another left-handed person. So because they're randomly selected and they're independent events, we know that this is going to be equal to the probability of L times the probability of L. Well, the probability of a left-handed person would be 0.13 or 1300ths, and be times 1300ths. And so you're going to get 0.0169. Now, keep in mind, they started by telling you a percent, and we could change this to percent. It just depends on how they ask the question in the homework. So this could be written as 1.69% or 1.7% if they wanted you to round to the nearest tenth of a percent. But we'll just go with the decimal answer for now. Okay, so go ahead and look at number 8 and think about what that would look like. All right, I'm going to assume you already gave it a shot here, and let me just put up a solution. So we said it could be more than 2 events. In fact, it's H and H and H, a bunch of 8 H's. So it's equal to the 8 probabilities here. Did I count 8? I think I did. All of these probabilities of H multiplied. Well, basically, we don't normally write it out like this. We would just write the probability is going to be 0.5 because 5/10 is the probability of getting heads. Because half the time you would get a head, half the time you get a tail. And since there's 8 of these products, we would take it to the 8th power and we get 0.0039. Or again, actually we would definitely write that one as a decimal. All right, so let's move on to the next concept here. And that would be computing at least probabilities. Usually, probabilities involving the phrase at least use the complement rule. Remember, the complement rule was that the probability of E complement is equal to 1 minus the probability of E. Remember, at least means greater than or equal to. So let's look at example 1. About 13% of the population is left-handed. If 2 people are randomly selected, what is the probability that at least one is right-handed? And I'm going to go back to what we were doing on the other worksheet because this problem is there. Let's look at number 4. So in this problem, so let me just read the question one more time. If 2 people are randomly selected, what is the probability that at least one is right-handed? Well, in this problem, at least one is right-handed is the complement of both are left-handed. So let's look at all the possibilities. So we're saying at least, we're basically, let me go ahead and do probability at least one is right-handed. So that's the probability we're trying to find. So at least one is right-handed. Well, let's look at the possibilities here. Because we're randomly selecting 2 people. We could get that they're both right-handed, and so that would be at least one is right-handed. We could get the first one right-handed, the second one left-handed, and it doesn't matter which order we do these. We just want to make sure we get all the possibilities. We could get a person that's left-handed and then right-handed, or again, they could both be left-handed. So when we say at least one is right-handed, that's these guys. So if this is E, I should say if, whoops. Let me be careful how I say this here. When we say at least one is right-handed, that's these here, which is the complement of both being left-handed. So if you have two that are left-handed, that would be your event where two are you pick two and they're both left-handed. This would be E complement here. And so let's see, what is the probability that at least one is right-handed? Well, it's going to be the complement of, I should say, this would be E complement, and so this is going to be 1 minus the probability of E, where E is the probability that they're both left-handed, so L and L. Well, we already found the probability that they're both left-handed. That was 0.0169. And so this is 1 minus 0.0169. And I'm running out of room here. This is going to be 0.9831. 0.9831. All right. So see if you can figure out how to do number two. Two. It's going to be very similar to the one we just did, and then watch the video. All right, so here we want the probability of flipping tails at least once. So you flip a coin 8 times. What's the probability of flipping tails at least once? And think about what would be the complement of flipping tails at least once. So the probability of flipping tails at least once. So that's our E complement, is 1 minus the probability of E. What does it mean to not flip tails at least once? Doesn't that mean that all 8 times you got heads? So it's 1 minus the probability of 8 heads. So we flip it 8 times and we get heads each time. So you could say H and H and H 8 times. I'm just going to say H, 8 heads. And in fact, we found that probability earlier. So this is 1 minus, it was 0.0039. That was problem number 3 up here, which I had the answer on earlier, but so I guess I can put it up here. We had gotten 0.0039. So here, 1 minus 0.0039, we get 0.9961, or 9,961 ten-thousandths. Okay. All right, so we're going to do 2 more problems, and these are some problems like what you're going to see the homework, and these are challenging. Similar to what we've done here, so we're going to do some stuff that's a little bit similar, but definitely a little bit different too. So let's go ahead and we'll just continue on this worksheet. In airline applications, failure of a component can result in catastrophe. It should say a catastrophe. As a result, many airline components utilize something called triple modular redundancy. This means that a critical component has 2 backup components that may be utilized should the initial component fail. you basically got 3 shots. One of them has to work. Suppose a certain critical airline component has a probability of failure of 0.0064, 64 10,000ths, and the system that utilizes the component is part of a triple modular redundancy. Assuming each component's failure or success is independent of the other, so we're assuming independence, what is the probability all 3 components fail? Which would be a disaster, right? So the probability of fail and fail and fail is equal to, well, we're just going to multiply the 3 probabilities. Well, and the probability that they fell is 0.0064. So we're basically taking that to the 3rd power, and we get a very small number. It's 0. And it's going to be 6 zeros, 1, 2, 3, 4, 5, 6, and then a 2, 6. So that's what you should get if you round to 8 decimal places, which is what you'll do in the homework. So that's the probability that all 3 fail. So it's a very small chance, which is what you want when you're dealing with a plane flying. Part B, what is the probability at least one of the components does not fail? So think about what is the complement of that. So we want the probability at least one does not fail. So I've called this E complement. It really doesn't matter which one I call E or E complement. I'm going to go ahead and call it E complement still just because of the formula. So what is, if E complement is at least one does not fail, what does it mean for that not to be true? At least one does not fail. So in other words, you've got so we're looking for the probability at least one does not fail. So the complement of that would be that they all fail. So it would be 1 minus the probability all 3 fail. Well, that's what we just found up above. So 1 minus 0.6 zeros and 2, 6. And if you subtract that, you get 0.999, 3 more 9s, so a total of 6 9s, and then 7 4. Again, round to 8 decimal places. All right, we've got one last problem to look at. For a parallel structure of identical components, the system can succeed if at least one of the components succeeds. Assume that components fail independently of each other. So again, we have independence, and that each component has a 1500s probability of failure. What is the probability that a parallel structure with 2 identical components will succeed? This is an at least statement, think complements. So we want to find the probability of, let's see, 2, where we go here. What is the probability that a parallel structure with 2 identical components will succeed? Well, it will succeed if at least one of the 2 components succeed. So at least one succeeds, doesn't fail. So let's look at what that means. At least 1 succeeds. So what are your possibilities? You could get succeed and succeed from the two components. You could get fail and succeed, or succeed and fail. And so that would be the cases where at least one succeeds. What's the complement of that? And again, really these are complements of one another. That would be if they both fail. So if we want to find the probability at least one succeeds, it's 1 minus the probability both fail. Well, that's going to be, let's see, we need to find the probability of fail and fail. Whoops. We need to know the probability they both fail. Well, that would be 0.15 times 0.15, which is 0.0225. And so this will be 1 minus 0.0225, and you get 0.9775. And so pretty high chance that they're going to be successful, that the system is going to succeed. Okay, in part B it says how many components would be needed in the structure so that the probability the system will succeed is greater than 9,999 10,000ths. Well, it's going to be just like what we just did here, but instead of having two failures, or at least, let me see, how do I want to say this? So in this case, we were dealing with two components. It's asking how many components we're going to need in order to get this kind of probability here. And so basically, we could look, we just did this one here, 1 minus 0.15 squared, and we got 0.9775, and that was for two components. What if it were three? Then we could do this here, and that's going to tell us the probability, if you have three identical components, the probability of success. So if you find that probability, you should get 0.9966. So that's not big enough. So let's do it again. Whoops, I'm sorry, you can't see that. So 0.15 to the fourth power, if you find that, you're going to get 0.9995. So we're getting close, but we're not quite there yet. And so we'll do it one more time to the fifth power. And when you round to 4 decimal places, you should get 0.9999, which is what we want. So we would need 5 components. So basically you have 5 of those to ensure that if some of them fail, that you're still going to have the system is going to be successful. Okay, so that's it for this video. I'm going to go ahead and stop it right there. Let me know if you need anything or if you have any questions.